Welcome to our talk about model-based testing with TLA and Apalache. This is a joint work of Igor Konnov and myself, and we both are proud to be members of Informal Systems, where Igor Konnov is a principal scientist, developing next-generation verification methods. He is also the leading developer of the Apalache model checker. And I'm a research engineer at Informal who also contributes to Apalache and leads the product on model-based testing.
We're using Rust and formal verification tools to build open-source, fault-tolerant distributed systems, like the Tendermint Byzantine fault-tolerant consensus engine and the inter-blockchain communication protocol. We're cooperatively owned and governed by our employees, and we have offices in Toronto, Berlin, Vienna, and Lausanne. In fact, a few other folks at Informal would love to say hello.
Hello.
Hello world.
Hi.
Hi everyone.
Hello.
Hey everyone.
Hello.
Hi.
Hey everyone.
You can learn more about us, check out our work, and contribute online at github.com/informalsystems. We hope you enjoy the conference.
Who we are. At Informal Systems, we envision the bright future of verifiable distributed systems and organizations. Nowadays, everything becomes distributed. And at the same time, when we interact with systems and organizations, we need a certain level of trust. Our grand vision is that formal verification can help us to bring this necessary level of trust to the systems and organizations with whom we interact. We actively contribute to this vision by developing the next generation blockchain infrastructure, namely the Tendermint blockchain consensus protocol and the inter-blockchain communication protocols. Our formal verification portfolio consists of the Apalache model checker, one of the leading model checkers for TLA+, and we also contribute to this verifiable organizations vision with the Themis contract tool. Our infrastructure powers the Cosmos network, and the Cosmos network is the dream vision of the next generation internet of blockchains, where each blockchain can operate independently. At the same time, these blockchains can interact and trust each other. How do we achieve this trust? We propose the verification-driven development framework. We have applied this framework to our own products, namely to the Tendermint family of protocols. We have developed English and TLA+ specifications of these protocols, model checked them with Apalache. This has helped us to fix some protocol issues, but most importantly, it helped to clarify the protocol understanding, the mutual protocol understanding between the research and the development teams. What's not so nice about this is that we have realized that after we start to develop code, the code starts to diverge from the specifications. You see that the necessary feedback loop is missing here. And the way we propose to address this issue is by model-based testing. In model-based testing, we generate integration tests from simple TLA+ assertions. This helps us to eliminate this divergence between the spec and the code. They now evolve in sync, and this significantly improves ease of writing and using the tests. Also, it improves the test maintainability and helps us to achieve higher code coverage. This is a teaser of our model-based testing process, but before diving into it, Igor will tell you more about the Tendermint protocol, the Lightline protocol, and the Apalache model checker.
Hey, my name is Igor Konnov. I'm a principal researcher at Informal Systems, and I will give you a brief introduction into Tendermint Light Client, how it's specified in TLA+, and I will give you an introduction in the model checking results with Apalache. And then Andrey Kupriyanov will continue the talk with model-based testing. So let's have a look at Tendermint blockchain. What is that? That's a sequence of blocks, and every block has a certain structure. So there are interesting fields here. One of them is a validator set. This is a set of computers that are going to vote on this block. And when more than 2/3 of them voted on the block, this block is going to be added on the blockchain. So there is an algorithm which is called Tendermint consensus, and all of these validators are running this algorithm. So what these validators are deciding on, they decide on the contents of this block, say application state in this block. They also decide on who the next validators are going to be. And when they have decided that, the validators change. The set of validators may change. When this block has been committed, there is another record that is formed in the next block, which is called last commit. This record contains the votes of the validators from the previous block and the hash that is pointing to previous block. So if you are running Tendermint consensus as a validator, you can make sure that your transactions that you have submitted on the blockchain, you can figure out whether they have been committed or not. But what happens if you just have a smartphone? You cannot run Tendermint consensus on it. It's just too expensive, and you don't want to invest a lot of money into running a validator. So that is the question the Light client is solving. So in the Light client, you have some trusted blocks, say block 1, and it doesn't matter how you figure it out whether to trust it or not, but you know you can trust it. And then you want to download another block that is far on the blockchain. You cannot trust anyone. You cannot trust the peers that give you the blocks, right? You have to use some knowledge about this blockchain to figure out whether you can trust the block. What can you do? The obvious solution would be, say, if you want to download block 9, the obvious solution would be to download the whole blockchain, check all the digital signatures, check how many validators have voted for each block, and so on and so forth. But that's too expensive, especially if you do it on a mobile phone. Fortunately, we can do what is called skipping verification, and it's using the knowledge about how this consensus is working. First of all, there is one interesting observation here. If I know that my block was committed by a set of validators, and more than 1/3 of these validators, if they were validators in a trusted block, then I know that at least one of the validators can be trusted because we have less than 1/3 of faulty validators in our system. So that's basically the idea. If you find a pair of blocks such that you can establish this root of trust, you can trust a new block and then do bisection again and find these pairs of blocks that can establish the trust. So basically, skipping verification is doing some form of bisection. There is one complication though. First of all, I have to make sure that more than 1/3 of validators has voted. And second, I have to know something about time, because in Tendermint, you don't put your money at stake forever. You put it for some time, which is called onboarding period. If I'm running a validator for, say, block 1, it means that I have staked some money, and this money is going to be lost if I do something wrong on the blockchain. That's why it's not sufficient just to check how many validators have voted. You also have to figure out that all these validators are still within what is called the trusting period. So you have to find that more than 1/3 of validators has voted, and your time is still within the trusting period of those validators who have voted on the trusted block. As we have seen, Tendermint consensus, the assumptions about the blockchain, and the Light client protocol, they're not simple. That's why we have decided to formalize all these assumptions in TLA Plus and check them with a model checker. But before we actually sat down and wrote a TLA Plus specification, we wrote another document which we call an English specification. That's how we do things at Informal Systems now. We write this document. It's a mixture of English prose and mathematics. It contains the sequential statement about the problem we are going to solve. It contains a decomposition of this problem into distributed components. It also has basic specifications of the temporal properties we believe this protocol should satisfy. And it has the high-level functions, the preconditions, the postconditions, and more importantly, the error conditions that tell us what has to happen if some assumptions about our system are violated. We use this document as a base for discussions between the distributed system engineers, verification engineers, and researchers before we start diving into a formal specification such as one in TLA+. I'm not going to give you this document here, but you can find it on the web. Here's a link, and you can see how one can understand this light client protocol without knowing TLA+. Once this document is ready, we sit down and write a specification in TLA+. In case of light client, it actually took us several hours to translate the English specification into actual TLA+ that we could check with Apalache. What we focus on in the TLA+ specification, we focus on the model of the blockchain that I briefly explained to you before. This model captures these notions of validator sets, Byzantine faults, and the time assumptions that we have in Tendermint consensus. And we have a specification of the light client protocol in TLA+. In our case, the light client protocol is talking to a peer. We know whether this peer is correct or faulty, and it also has some time that it relates to the blockchain. Again, I'm not giving you the TLA specification. You can find it on the web, but I want to give you a bit of flavor about this specification. So first of all, the light client can talk to either a faulty peer or a correct peer. The light client, of course, cannot know whether the peer is faulty or not, but we set up a parameter in the specification that is telling us whether the peer is faulty or not. If the peer is correct, we just copy a block from the blockchain and give it to the light client. If the peer is faulty, we produce a non-deterministically block that passes some basic validation tests, but it might have the incorrect set of validators, or it may have an incorrect set of commits, it might have some skewed time, and so on, so forth. I just want to show you here the structure of the blocks that we have, because that might be interesting. So blocks are basically records in TLA. They have the height, the time, which is just an integer in our encoding. They have a set of commits. These are the validators who have voted on the previous block. They have the set of validators for the current block, and they have the set of validators for the next block. When a client is receiving a light block, it gets this header plus the set of commits who must have voted on that header. And if you think about checking this data structure with TLC, imagine you have a sequence of blocks like that. You can see that there is a lot of space for state explosion here. You have integer time, and you have 4 sets of validators. That's why we are using Apalache. Again, I'm not giving you details, all the details here, but basically, before we run the light client, we initialize the blockchain is just in one step. And the way we initialize it, we just guess the validator sets, the sets of commits, and timestamps. So they form actually a correct blockchain where more than 2/3 of validators have voted. Commits are also correct and not corrupted, and timestamps are growing monotonically. Let's see how we can verify the TLA specification of the light client with our model checker, Apalache. If you have never seen this tool before, you can go on that web page that's mentioned above, read the manual, and see for yourself how to is working. From the bird's eye perspective, what it does, it takes a TLA specification, it unfolds all the operator definitions, including the recursive operator definitions up to certain bounds. It finds what we call assignments, similar to what TLC does dynamically. It decomposes a specification into smaller pieces that we call symbolic transitions. They roughly correspond to actions in your specification. Then it does some simple type checking, although what it does now is going to be superseded by the new type checker and type infer you will heard about at this meeting as well. And then it does a translation of a TLA specification into an SMT formula. As you probably know, SMT solvers are quite powerful, and we want to utilize their power for verification questions in TLA+. What Apalache does in a bit more detail, it actually performs bounded model checking. Given a specification in the following canonical form that TLC also expects, Apalache first checks whether the invariant can be violated in the initial state, translates this formula into SMT, and tasks the SMT solver if it can find a satisfying assignment for this query. If it has found a satisfying assignment, Apalache will produce a counterexample in TLA form. Otherwise, it will continue to unroll the executions. It will introduce 1 step, 2 steps, 3 steps until it has either found a counterexample with SMT or it has reached a certain depth. That's why it's called bounded model checking. Fortunately for the light client specification, we even can provide a depth given the length of the blockchain. We ran Apalache on different models produced from the light client specification. There we had from 4 to 7 validators and from 3 to 5 blocks in the blockchain. Also, we had either faulty or correct peers the light client was talking to. These are not huge numbers, however, recall that we had all these power sets in the blockchains and tricky relations, including cardinality comparisons. We also have found some violations of the properties, which is interesting because these violations were predicted by our researchers. And I just want to show you how Apalache runs. Without any compilation or whatever, you can just pull the tool from Docker. It will pull a Docker image. In my case, it's fresh, so it doesn't do anything. And then I run the Docker image. I run Apalache in the Docker image. I ask it to check this invariant and give it the model of 5 validators and 5 blocks. What Apalache does now inside the Docker image, it does the preprocessing I told you about, and then it checks the invariant for the initial state, for the states, all possible states after 1 step, after 2 steps, after 3 steps, and soon it's going to report a counterexample. Yeah, so here's a counterexample. You can go to counterexample.tla and see the exact values produced by Apalache and Z3 that violate this specific invariant. Now I give the floor to Andrey.
Now we continue with the model-based testing, but before diving into it, I want to describe shortly how standard testing looked for us before. A test engineer was using the Tendermint and Go implementation to manually write integration tests that were then run against both Tendermint and Rust and Tendermint and Go implementations. This is an example of a pretty simple manually written integration test. It just constructs a test case, which is a sequence of steps for the light client protocol. Then this test case is translated into the JSON encoding for all the necessary data structures, which contain such details as public keys and hashes, and is executed by the static driver. And this static driver is a pretty simple piece of code which just takes this test case executes the light client verifier and compares the verdict that it returns at each step with the verdict that's expected from the test. Standard testing has a number of drawbacks. First of all, it's manual generation. It's lots of effort. This test that we saw was pretty simple, actually. In more complicated cases, it's non-trivial logic required, and it's inflexible. It fixes all the parameters. Non-determinism left for exploration. It's also hard to understand what a particular test case does. It's hard to maintain them, and it's hard to cover all the cases because we need hundreds of those tests. That's why we switched to model-based testing. And now we will look at its components. But before looking at it in particular, we'll run a short demo. This is a short demo of how our model-based testing is working. It's fully integrated into the standard cargo test command as a test. So when we run this cargo test command, what happens? For each of the TLA plus tests, in this case the test success, it runs Apalache on this test. Apalache produces a counterexample which contains the example execution. This execution is then translated into the static test, and this test is run against the implementation. In this case, we have the light client protocol, and we execute this light client protocol against the static test and compare the verdict that we obtain against the expected verdict. What we can see in this case is that running Apalache does take some time, but as a byproduct of those model-based tests, we obtain the static tests, and this static test can then be executed independently in almost no time. Now, how does a TLA plus test look like? TLA plus test is a pretty simple TLA plus assertion. You see, it's very easy to understand for each particular test what it does. I very much like, for example, this test. This test says that for each state in the computational history, the validator sets should be different. You can also express assertions about time, for example, or about the final state of the protocol. How do we integrate these tests with the light client model you saw before? This is also very easy due to the modular nature of the TLA plus language. We simply extend the init and next predicates with the history tracking. So we introduce this additional history variable, and this variable just tracks the necessary state components of the light client protocol. And at each step of the model execution, besides executing the model itself, we are also updating the history for the next state. For the model checker, we needed only to extend it with JSON input-output support for integration purposes. In fact, you can now use Apalache as a translator between TLA plus and JSON, and we highly encourage everyone interested to use this feature. You could use it, for example, to integrate TLA plus with your tools. Now, how counterexample looks like. A counterexample is a sequence of history states. At each state of this history, we have the current block, the current time point, the verdict that we expect from the light client, and the latest verified block. And this is how a small portion of this history is translated into JSON. Don't be scared by the large size of the encoding. This is meant only for automatic processing. Now, as a next step, we transform our counterexample with the help of another component which is called JSONator into the static integration test. And this transformation happens with the help of so-called transformation specification, which is a small domain-specific language which describes how to transform one JSON into another JSON. An important part of this translation is that it calls so-called Tendermint Testgen command, which allows us to produce full Tendermint data structures from the abstract data structures that we have in the TLA plus model. Let's take a look how Testgen works. Effectively, you can see it as a probe into the concrete implementation space from the abstract TLA plus space. For example, in the abstract space, a validator is a simple string identifier. In the concrete implementation space, it contains private and public keys and additional details. A header in the abstract space just lists all simple abstract details, like the validator set, the next validator set, the height, the time, and last commit. And this translates into a fully fledged data structure with all the necessary hashes. Now to the results. One of the most important results about model-based testing is, from my point of view, that it helped to eliminate the divergence between the spec and the code. Each case that you see here results from a failing model-based test. For example, it was able to catch such corner cases as the difference between less and less than or equal. In this particular case, the specification, the TLA plus specification, actually diverged from both from the English specification and from the source code. In another cases, we added, for example, additional condition to the specification because it was generating negative times because it was simply integers. And then another corner case between less than or equal and less. And it was also missing another check in the specification that the headers are not coming from the future. Model-based testing helped us to substantially improve the code coverage, as you can see, for the relevant parts of the source tree. And it already helped us to find the real bug, although this is only the first iteration. Recently, we have updated the Tendermint protocol from version 0.33 to version 0.34, and the validator set ordering changed between the versions. An important aspect here is that this bug was missed both by the standard testing and it was also not properly documented in the specifications of the protocol, but it was caught by the model-based test. It was a pretty simple fix, as you can see here. Now, to conclude, model-based testing substantially improves ease of writing and using the tests. It's much easier to maintain them, and it improves the code coverage. The most important aspect, I think, is that it makes the specifications live. Now, specification evolves continuously with the code that it specifies. And although we have invested some time into infrastructure, I think the benefits substantially outweigh those investments. As a future work, currently we are working on adding fuzzing to model-based testing. Under fuzzing, we understand additional mutation on the level of data structures. And this allows us to cover scenarios which are currently inexpressible in the abstract model. For example, in the abstract model, a validator set is a mathematical set, so it can't contain two identical validators. At the same time, for the source code, you want to test such cases. We plan to add extensions to the Apalache model checker for faster counterexample search because counterexamples can be found using specialized techniques. Currently, Apalache is more targeted towards invariant checking. We plan to generate executable code from TLA plus specifications, and this means just resolving all non-determinism that is present in the TLA plus. This will allow us to substantially speed up testing, and we plan to extend the model-based testing framework to distributed setting, where we will cut the system at the interface points and replace some of the models with executable specifications, and in that way, we will test a mixture of the specs and the real code in the running system. Thank you for your attention.